Arc length, estimating graphically and solving algebraically. So if you have a circle, this is one in which this central angle here is 75 degrees and the radius is 6 feet, then what is the length of the minor arc here in green? Well, let's estimate it graphically. The radius is 6, so estimate the length of that arc. Think about it. What do you think it is? Sure, it's about 7 or 8 feet long. So let's do the algebraic solution. So the algebraic solution is part is to whole, part is to whole. The arc length is part of the circumference to the entire circumference equals this angle, the central angle, to all the way around. If we were doing this in radians, we would do arc length is to circumference as angle is to 2 pi. But anyway, we're not doing it in radians, so we'll use angle over 360. So the circumference is 2 pi r. So the arc length is to 2 pi 6, as 75 degrees is 360 degrees. So solving for arc length, we get 12 pi times 75 degrees over 360 degrees. And the approximation for that is about 7.85 feet. And fortunately, that answer makes sense. If you do the algebraic solution and you get to an answer that doesn't make sense, but according to your graphical estimation, it's likely that you made a mistake in your algebra, and then go back and find the mistake. So the traditional approach to this is S is equal to arc length, theta is equal to angle. And notice in degrees you come up with a pretty messy formula. If you do the same thing in radians, you end up with S equals r theta. This is the traditional approach to arc length, but you have to stipulate that theta is in radians. So if you're given the problem in degrees, you have to convert to radians. So it's two different approaches to the problem. One is a part is to whole problem where it doesn't matter whether it's in degrees or radians. The other, more traditional approach is S equals r theta, but you have to convert all angles into radians.